Okay, I want to continue from where we left off on Friday's lecture. We were talking about section 2.2, basic differentiation rules and rates of change. And we had three differentiation rules already. The derivative of any constant equals 0. We worked that one out using the limit definition of derivative. The derivative of the function x is 1. We also worked that out using the limit definition. Limit as h goes to 0, f of x plus h, and so on. And the derivative of x to the n equals n times x to the n minus 1. Remember, this is called the power rule. And we use it on power functions. I want to give you some more rules today, in addition to talking about rates of change, and then we'll finish this section up on Wednesday's class. So the next rule I want to give you is the derivative of an exponential function. So let's just do e to the x to start with. The derivative of e to the x is just e to the x. And I'll include this as a separate rule. The derivative of any number raised to the power of x is the natural log of a times the original function a to the x. That's the same as that, and all you do is put a natural log of a in front of it. So this is probably the most common error that students who are first learning to take derivatives make. Let me illustrate my point. Let's say I want you to take the derivative and I'll give you two functions here. One will be x to the, let's make it 5. And the other one will be 5 to the x. These are two completely different kinds of functions. Two completely different kinds of functions. This first function is a power function. Power function has the variable downstairs in the base, and then it has a constant exponent. This function is an exponential. The variable is upstairs in the exponent, and the constant is down in the base. And when you take the derivative of the first one, which is a power function, x to the some power, you use the power rule. So f prime of x equals, we bring the 5 down just like we did last time, x to the 5 minus 1, or 4. 5x to the 5 minus 1. 5 minus 1 is 4. Power rule for a power function. This students generally get correct. It's this one that people generally get wrong. And the part they get wrong is they try to use the power rule on an exponential function. Please try never to use the power rule on an exponential function. You don't want anything that looks like this, x times 5 to the x minus 1. I shouldn't even write that on the blackboard, because that's completely garbage. That doesn't make any, that's just not right. Instead, what we have here is an exponential function where the variable, where the base a is, in this case, 5. So taking the derivative of an exponential function is pretty easy. You just write the original function, a to the x, just like you had it before. So 5 to the x. And then in front, behind, wherever you want to put it, I'll put it in front, you put the natural log of the base, natural log of 5. It's just the original function times the number natural log of 5. Natural log of 5, you can type that into your calculator. That's a number. So natural log of 5 times 5 to the x. Don't try to use the power rule on an exponential function. Feel free to move the video back and play that sentence over as many times as you want till it makes sense. This is a power function. We can use the power rule on it. This is an exponential function. We use, if you want to give this thing a name, you can call it the exponential rule. And I said the derivative of e to the x is e to the x. These two are compatible. This is the more general of the two. If you want to try to use the second one on e to the x just by saying the base is going to be e, you could do that. H prime of x. You could just go ahead and write down e to the x using rule number 4, but if you wanted to use rule number 5 on it, that's fine. You would just write the natural log of e times e to the x, but the natural log of e, that says the number you have to raise e to get e, well, you raise it to the power 1. So natural log of e, that's just 1. So this is just 1 times e to the x. In other words, e to the x. But you might as well just use the derivative of e to the x as e to the x. Rather than taking 3 steps to get there, we might as well just jump right to the answer. So hopefully that made sense. There are 2 more rules I want to talk about today. The first one is this: the derivative of any constant times a function. So this is not a constant sitting by itself the way it was up here. Is just that constant times the derivative of the function. And I'll explain that in just a couple of minutes after I introduce the next rule. So in other words, you can pull constants back and forth through the derivative. So the next rule is that the derivative of f of x plus g of x equals the derivative of f of x plus the derivative of g of x. And that works with minuses too. Let me just look on the screen to see if that's clear enough. Yep, I can see the top of the screen's a little bit blurrier than I like. I don't know what's up with the webcam, but the bottom of the screen looks pretty good. So we have these 2 rules. We've already seen rules like this once when we were talking about limits. We see them now again with derivatives. We will see them again later in the course when we talk about antiderivatives. These 2 rules always travel together, and together they're known as linearity. Let me illustrate what these 2 rules mean. So let's say we're still taking the derivative. We did it parts A, B, and C. Let's do D. Let's say I have f of x equals x cubed plus 5x squared plus minus 2x plus 1. This first rule says that I can just break the derivative up. If I want to take the derivative, f prime of x equals, so I don't write just equals because then I'm saying the derivative is equal to the original function, which of course it's not. This is a new function. Every time we take the derivative, it's a new function. This just says I can take the derivative of these parts that are connected by plus signs and minus signs separately. That's what Rule 7 does. All this, if this looks like algebraic nonsense, that's all it says. So this is just the derivative of x cubed. I'm going to put a prime there to remind me to take the derivative in the next step, plus the derivative of 5x squared. I'll put a prime there to remind me to take the derivative in the next step, minus the derivative of 2x. I'll put a prime there to remind me to take the derivative in the next step, plus the derivative of 1. So I'll put those primes in there. So now I've jumped back from Leibniz's notation and Newton's notation. I'm using Newton's notation over here right now just because it's shorter. I don't have to keep writing the ddx. Okay. Now, instead of having an x squared in this term and an x in this term, we have a 5x squared and a 2x over here. This rule just says I can pull this 5 out of the derivative, and I can pull this 2 out of the derivative. So let me just illustrate that. I'm still not going to take the derivatives of the inside parts. X cubed prime. So these are not 1s outside, these are primes to take the derivative. Plus, move the 5 outside. The derivative of x squared minus 2 now it's outside, x prime plus the derivative of 1. Now let's go ahead and take the derivatives of those inside bits. Derivative of x cubed, we know, according to the power rule, is 3x squared, plus 5 times the derivative of x squared. We know the 2 comes down, x to the power 1. I'm not even going to write the power 1. It's not necessary. 2x minus 2 times the derivative of x, we know is 1, plus the derivative of 1 is 0. You don't even have to write the plus 0 if you don't want to. And now I have 3x squared plus 10x minus 2 plus 0, if you like. Now, in very short order, certainly by the end of doing a few practice problems on this, maybe already, you're not going to write all this intermediate nonsense. You're going to jump right from this step right to this last step and do this all in one step. The derivative, so you're going to remember, sort of intuitively speaking, that the derivative breaks up over plus signs and minus signs. All you have to do is take the derivative of each of those parts separately. And you're going to remember that these numbers in front of the x squared and the x just sort of hang around out front and multiply whatever comes down. So derivative of x cubed, 3x squared, the 3 comes down, you write the x, the 3 becomes a 2, 3 minus 1 is 2, plus derivative of x squared is 2x, so the 5 hangs around out front, 5 times 2 is 10, x to the 1, derivative of, so minus, the derivative of x is 1, but there's a 2 in front of it, so minus 2. Derivative of 1 is 0. You jump right to the answer. I can't see any of you doing this more than once or twice in your entire life before it comes automatic. Maybe a few more times. But it's almost easier just to jump right to the answer. But that's all you're doing. This just says break things up over plus signs and minus signs. This says constants in front of things you already know the derivative of. Just hang around up front, multiply what's ever there. So distinguish this from this. Here we have a constant by itself, derivative of that 0. Here you have a constant in front of something else. And that's it. See you Wednesday.